Morning class, we're going to go over 5.3 concurrent lines, which we'll go over what concurrent means, medians and altitudes. So we'll start off with a couple things. First of all, we're going to identify a number of properties that go with concurrent lines. And so we'll start there. So first of all, what does it mean to be concurrent? It's where three or more lines meet together. And that would be a line of, or a point of concurrency. So where those lines meet would be the point. Circumcenter. So circumcenter is the center of a the center of a circle that would go around a triangle. So if you have a triangle, you can put a circle around. It would touch each vertex, and the center of that circle is what we call the circumcenter. If you were to draw it around, we call that to circumscribe. If it's inside the triangle, it'd be inscribed. So circumscribed goes around a triangle, and we'll look at properties with that, and then we'll also look at an inscribed triangle as well. So here we go. Here's what we call the perpendicular bisectors of the sides. So if you look at these lines right here, those are the bisectors of our, here, and I'll zoom in just a little bit so you can see. Okay. There we go. So if you look at it, a couple things we can look at. So here, these right here are the perpendicular, meaning right angle for each one of these, and they bisect each side. You can see they cut it into equal parts. We have the congruent markings right there. So the perpendicular bisectors of the side are equal distance. So that point where they all meet, they're equal distance from each vertex. And where they meet, that point of concurrency, that gives us the center of a circle that would circumscribe, go around our triangle. You'd see it hits right at each point. So that's what we're looking at. So that's our first property, that the perpendicular bisectors, so these lines, where they meet, that point of concurrency, is equal distance from the vertex on each spot. So we're going to go ahead and do an example with this. So what we want to do is we want to go ahead, there we go, is we want to find the center of our circle that you can circumscribe about the triangle. So that would go outside of our triangle. So first, let's just plot the points. So 0, 0, we plot 0, 0, negative 8, 0, and then 0, 6. And we have the triangle that forms right here. So what we want to do is we want to find the circle, the center of the circle that goes around. So what we have to do is we have to find the perpendicular bisector of each side. Now this is pretty easy. We have a right angle here. So if I come down here, a perpendicular bisector, so if I have a horizontal line, what's perpendicular to a horizontal line is a vertical line. So if I look at 1, 2, 3, 4, 5, 6, 7, 8. So I'd find the center of that. So you come over 1, 2, 3, 4. There's the center of this side. Then I come up here 1, 2, 3, 4, 5, 6. Find the center of 6, and that's at 3. So where they meet, where these two lines meet, is right here. Now, you don't need to find, I know we went through and said you need to have 3 lines of concurrency. Well, if you know where two lines meet, the third line is going to meet at that same point. So this point right here would be the center of our circle that circumscribes. So now we can draw. Now you just open your compass. You take out your compass. I'm not going to do it on here, but you just take out your compass. You put your compass at the center of your circle, and now you go all the way around. And you can see how it goes through this point here, it goes through this point up here, and it also goes through this point down here. So we would draw that circle on it, so the circle that I kind of just drew, and then we identify the center. The center is, if you look at it, it's over 1, 2, 3, 4, so negative 4, and then up 1, 2, 3. So the center of that circle would be negative 4, 3. Another theorem, the bisectors of the vertex of the angles, so they bisect here, splits these into equal parts, okay? The bisectors of a triangle are concurrent at a point equal distance from the sides. So if we look at it, and I'm going to zoom in on this triangle, okay? So now we have the angle bisectors, so these angles are now bisected, they're equal on each part. Where they meet, okay, is equal distance from the center, or is equal distance from the sides of a triangle. So this distance from here to here is the same as here to here, is the same as here to here. If you notice, that's the radius, it's touching. So this is the center of a circle, this is the radius to the outside of your circle. So yes, they should all be equal because it is the radius. So now we'll look at, there we go. The point of concurrency of an angle bisectors is called the incenter. So if you notice, we have a circle that goes inside of it, so we call this the incenter. When the circle went outside of it, we called it circumcenter. Circum goes outside, in goes inside. So let's go ahead and we want to find the variable. So we want to know what's the distance from here to here, that's y. We want to find the distance from here to here, that's x. Well, what do we know? What's the distance from here to here? Well, that's 4. So x would be the same. The distance from the center of the circle to the edge of the triangle is equal. So x would be 4. Also notice y would be 4. Y is from the center to the outside edge of the circle. So that's the radius as well, so that would be 4 as well. Now we want to find, okay, what is IC, the distance from I to C? Well, the distance from I to C is made up of y, and then this distance of 10. We already know what y is. Y was 4. So we would say IC is equal to 4 from here to here plus 10 more. So it'd be 14. Now we're going to go over a couple things. The median just goes from a vertex and it bisects the side opposite of that vertex. It's not saying that this circle, or that it bisects this angle, so we don't know that these parts are equal, but we do know that it bisects this side. So if this side were 6, this side would be 6. So that's the median, from the vertex to the opposite side, and bisects it. Now if we have medians, here's our property on medians. All right, the medians of a triangle, where they all meet, that the point is 2/3. So from here to here is 2/3 of the whole distance. So it makes G to D is 1/3. So that's our property. So if you can go through and you can look at it. So A to G is 2/3 of the whole line A to D. C to G is 2/3 of this whole distance from C to E. B to G is 2/3 of the whole distance from G to F. So what I do is I break it up into thirds. So here's an example. We want to find E to B. So let's first of all, we know C to E is 11, F to O is 10, C to O is 8. So let's list them all out. Again, we had C to E is 11, F to O is 10, and then we have C to O is 8. So now we're going to go ahead, so first of all, label. So we want to find E to B. E to B. Hopefully this one's not too bad. It's a median, so it bisects it into equal parts. So if this side's 11, then this side over here will be 11 as well. Now we want to find, and I'm actually going to skip, I'm going to find C to D. So I want to find O to D. Well, first of all, I'm going to find this whole distance. So just know, from here to here is 2/3 of the whole thing. So if I break it up into thirds, I'm just going to take 8 and divide it by 2. So 8 divided by 2, so if it's 2/3, I divide it by 2, and you're going to see me do a little bit of work over here. I'm going to just move it right here. So 8 is 2/3 of the whole distance. So all I do is I take 8 and divide it by 2. So 1/3, so 4, is equal to 1/3. Okay? So if I come back over here and look at it, so if 1/3 is equal to 4, then think about the whole thing. So if I break it up into a line, and we break it up into thirds, we'll go like this. We'll try to do as best we can. So we have 1/3 here, which is 4. We have 1/3 here, which is 4. We have 1/3 here, which is 4. So that's all I do, is I break it up in this fashion. Alright, so we can find out the whole distance. The whole distance is 4 plus 4 plus 4, which is 12. So now I'll go back here. So that's all I do, is I just think about breaking up as dividing it by 3. So that whole distance from C to D is 12 units. So now we'll go O to D. So we already talked about it over here. So we broke it up into 4. So we had 4 here, 4 here. So O to D is going to be 4 as well. Then we want to find, why didn't I do it? So now we find F to B. So F all the way to B. Well, think about it. From F to O is 1/3. So then this is 2/3. So another third would be 10, and another third would be 10 more. So we have 10 and 10, which is 20. So I have 20 plus 10, which is 30. So again, that's all I look about, is breaking up into thirds. O to D we went through was 4. So if A to O is 6, find O to E. So if A to O is 6. Again, that's the 2/3 part. So let me turn it over here. So this would be 6 is 2/3. So I divided by 2. Both sides you can divide by 2. And so this would be 3 is equal to 1/3. So once again, think about breaking the whole line up into thirds. Okay? So you have 3 here, that's a third, that's a third, that's a third. So you have 3, 3, 3. The whole line is 9. So anytime you get it, break it up into thirds and go from there. So if I want to find A to O, O to E, I just want this third here, which would be 3. Last few things, altitude. The altitude is a perpendicular, just from a vertex, meets perpendicularly. That means it just meets at a right angle. It doesn't say that we're bisecting the angle or bisecting the side. So if you have an acute triangle, it's going to be inside. If it's a right triangle, your altitude is right on this, the triangle itself. It's that side. If it's if we have an obtuse triangle, it's going to be on the outside. So last example. So what's the difference between an altitude and a perpendicular bisector? Well, an altitude doesn't have to bisect the side. So a perpendicular bisector is a right. It meets at a right angle and it bisects the side. Altitude doesn't. And so just the orthocenter of a triangle is where the altitudes meet. So if it's acute, it meets inside. If it's a right triangle, it matches on the triangle itself. And if it's obtuse, it'll meet on the outside. Okay, so what we want to do is we want to identify an angle bisector. Angle bisector bisects an angle. So when you look at it, we don't have congruent parts there. We don't have congruent parts there. We do have congruent parts there. So we'd identify our perpendicular, or just our angle bisector, bisects an angle, would be B to D, or D to B, either way. A median. A median, if we think about it, goes from the vertex to the opposite side and bisects that side. So if I look at A to K, goes from the vertex, but it doesn't bisect this side. If you look at J to H, it bisects the side, but it doesn't come from a vertex. You look at this one, so you could look at this one right here, or you could here, the median. Okay, the median goes from C to E. It bisects this side, so that's what we call a median. The perpendicular bisector meets at a right angle and bisects the side. So you have a right angle, bisects the side, so we'd say J to H is that. And then lastly, an altitude comes from the vertex and meets at a right angle. So from the vertex, no right angle. From the vertex, no right angle. From the vertex has a right angle, so we call it AK. So that's our lesson for today. We have in-center and circumcenter. In-center means our circle's inside the triangle. Circumcenter means the circle's outside our triangle. We had an altitude. Here we have an angle bisector, which is previously a median, which is today just from a vertex and bisects the side. Perpendicular bisector we had before, and then an altitude. An altitude is from the vertex, forms a right angle.